All right, let's get started. Welcome to another deep dive, and today we're tackling something that's pretty mind-blowing, the quantum internet.
Definitely a fascinating topic.
It really is, and you know what's even cooler? We're doing this deep dive based entirely on the quantuminternet.pdf document that you, our listener, sent our way. So this one's for you.
Always exciting to see what our listeners are curious about.
Exactly. Now, from the looks of it, you're really interested in the future of communication, maybe even teleportation. I mean, who wouldn't be, right?
Yeah, it's like something straight out of science fiction.
Totally.
Yeah.
So let's unpack this quantum internet.pdf document and see what insights we can glean from it.
Sounds like a plan.
Now, to really understand the potential of a quantum internet, I think we first need to grasp what quantum information even is.
You're absolutely right. It's a whole new way of thinking about information. We're moving beyond the ones and zeros that we're used to with, our everyday computers.
I'm all ears. Help me understand what makes quantum information so different from the bits and bytes we deal with every day.
So imagine a regular bit, like a light switch. It's either on or off, right?
Right.
Now, picture a quantum bit or qubit. It's more like a dimmer switch. It can be on, it can be off, or it can be anywhere in between. That's what we call superposition.
Whoa, so it's not just a 1 or a 0. It can
No.
be both at the same time.
Precisely. And it's this very concept that unlocks some really interesting possibilities. Like, imagine if you wanted to send a super secure message.
Okay, I'm intrigued.
With classical computing, you'd rely on complex algorithms that, while a really powerful computer could potentially crack. But with quantum mechanics, you could create a truly unbreakable encryption key.
Now you've got my attention. How would this quantum encryption even work?
Well, it all comes down to another fascinating property of qubits: entanglement.
Entanglement, what's that?
Think of it like this. You have two coins, and they're magically linked. If you flip one and it lands on heads, you instantly know the other will land on tails no matter how far apart they are. That's entanglement.
That's pretty wild. But how does that translate into secure communication? I'm not seeing the connection yet.
So imagine you and I each have one of these magically linked coins. We flip them at the same time, and boom, because they're entangled, we both know the outcome without needing to actually tell each other. It's like sharing a secret instantly, even across vast distances.
Okay, now that's a cool visual. But how does this help with encryption? Could someone just, intercept the coins?
But here's the thing. There's this fundamental rule in quantum mechanics called the no-cloning theorem.
No cloning theorem. Okay.
And it states that you can't make an exact copy of a quantum state. So if someone tried to intercept our entangled qubits, they would inevitably disrupt the entanglement. It'd be like setting off an alarm.
So it's like a built-in security system.
Yeah.
That's pretty clever.
It is, and it really highlights how entanglement could be the key to so many potential applications of a quantum internet.
Okay, so entanglement is like the magic ingredient here.
Yeah.
And it's not just about security, right? What other possibilities does it open up?
Oh, tons. For instance, it could allow us to build these incredibly powerful distributed quantum computers.
Distributed quantum computers. That sounds intense. What could we even do with those?
Well, picture this. You have multiple quantum computers all linked together through entanglement. It would be like having a supercomputer capable of tackling problems that are just impossible for even the most advanced classical computers today.
So we're talking about solving some of humanity's biggest challenges, like
Yeah.
with developing new medications, new energy sources.
Exactly, and that's just scratching the surface. A quantum internet could also lead to breakthroughs in other fields, like atomic clocks and telescopes, pushing the boundaries of measurement and precision even further. But of course, building this kind of network is, well, let's just say it's no walk in the park.
That's what I was wondering. This all sounds incredible, but what are some of the challenges we'd need to overcome to actually build a quantum internet?
Well, for starters, quantum states are incredibly fragile. I mean, think of them like tiny little snowflakes. The slightest disturbance can cause them to collapse, which makes transmitting them over long distances really, really difficult.
So we can't just send qubits through fiber optic cables like we do with normal internet data.
It's not that simple. We need to develop new ways to transmit and amplify these super fragile quantum states without messing them up. And remember that no cloning theorem we talked about? Well, that means traditional repeaters, the ones that amplify signals by making copies, just won't work in the quantum realm.
So it's like trying to send a snowflake across the country without it melting or breaking.
Exactly. It's a real challenge, but researchers are already coming up with some pretty ingenious solutions, like using special diamond crystals to store quantum information, or even creating photonic repeaters that work entirely with light.
Diamonds and light. That sounds almost magical. It seems like we're still in the very early stages of developing this technology.
Oh, we are. But the progress being made is exciting, to say the least. And speaking of exciting progress, you know that quantuminternet.pdf document you sent? Well, it mentions this really cool approach to storing entangled states. They use clouds of cesium atoms. It's like creating a quantum hard drive.
Whoa, a quantum hard drive. Now that's something I'd love to see in action. But, before we get too carried away with the future, let's take a closer look at something else that caught your eye in that document. The discussion about nuclear energy and thorium reactors in particular.
Oh, yes, that's something you're clearly interested in. It's a complex topic, for sure. But it also has huge potential for addressing our energy needs in a more sustainable way.
Absolutely. It seems like you're especially drawn to the potential of these thorium reactors. What about them piqued your curiosity?
Well, from what I've read, they offer some significant advantages over traditional uranium reactors. For example, they produce far less radioactive waste, which is a big plus, and they also have a much lower risk of, well, let's just say misuse, which is always a concern with nuclear technology.
That's definitely good news. But I have to admit, I still have some concerns about nuclear energy in general, like the possibility of accidents or the whole issue of safely disposing of nuclear waste. It's hard not to think about those things.
Those are valid concerns. They need to be carefully considered, no doubt about it. But it's also important to remember that technology is constantly evolving. Newer reactor designs, like the pebble bed reactor mentioned in the document, offer enhanced safety features that could potentially mitigate some of those risks.
Pebble bed reactors. I've heard the name before, but I'm not really familiar with how they work.
So imagine a reactor core that's filled with these thousands of tiny graphite spheres. Each one contains nuclear fuel. These pebbles, they're actually pretty ingenious. They act as both fuel and moderator, controlling the nuclear reaction and making the reactor much safer.
That's amazing. It seems like we're potentially on the verge of some major breakthroughs in both quantum information and nuclear energy. I mean, it's incredible to think about how these advancements could shape the future, right?
It really is a fascinating time to be alive. It's hard to even imagine what other groundbreaking technologies might be just around the corner. Who knows what the future holds? But for now, let's focus on something that really caught your attention. Quantum teleportation. I mean, it sounds like something straight out of Star Trek, doesn't it?
It totally does. I'm still a bit skeptical, to be honest. Is it really possible to teleport information from one place to another? It just seems too good to be true.
Well, let's break it down and see if we can make it a little less mysterious. Remember those entangled qubits we talked about earlier? The ones that are like magically linked?
You mean like those coins that always land on opposite sides?
Yep, exactly like that. So imagine we want to send a message, a piece of quantum information from one location to another. We could encode that message into the state of a qubit.
Okay, so the message is basically represented by the state of this qubit.
Okay.
Got it. What happens next?
All right, so we take our message qubit and we entangle it with one of the qubits from that entangled pair. Then we do a very specific measurement on both the message qubit and our local entangled qubit.
Hold on. A measurement. What does that actually do?
Well, remember how when we measure a qubit, it kind of forces it to choose a definite state, collapsing that superposition?
Right.
Well, since our message qubit is entangled with one of those qubits in the pair, measuring it has this spooky effect on the other qubit, the one that's far away.
Spooky action at a distance. Now, it really does sound like magic.
It does, right. But trust me, it's real science. The measurement we take on our local qubits, it instantly affects the state of that distant qubit, even though they're not physically connected. It's mind-blowing.
So, does this mean that the information from the message qubit has been instantly teleported to that distant qubit? Did it just, poof, disappear and reappear?
Not quite. That's where things get a bit tricky. See, the measurement itself doesn't tell us what the message was. Instead, it gives us a set of instructions, a kind of quantum recipe, if you will, that we need to send to the recipient along with the entangled qubit.
Oh, I see. So we still need to send some regular information like a text message or an email to actually complete the teleportation process.
Exactly. And that information still has to travel at the speed of light, so it's not instantaneous. But get this, the message itself never actually travels through space. It disappears from one spot and reappears in another without ever crossing the distance in between.
Wow, that's truly incredible. So, Even though we're not beaming objects across space like in Star Trek, we're essentially teleporting the information encoded and encrypted.
You got it. And this ability, the seemingly magical ability, has the potential to completely change communication as we know it.
Well, we've certainly covered a lot of ground in this first part of our deep dive. From qubits and quantum teleportation to the potential of thorium reactors, it's clear that we're on the cusp of some really transformative technologies.
Absolutely. It's an exciting time to be following these advancements, and who knows what other amazing discoveries lie ahead.
Welcome back to our deep dive into the quantum internet. I don't know about you, but I'm still processing that whole teleportation thing. It's just wild.
Yeah, it really stretches the imagination, doesn't it? And that's just one of the many things a quantum internet could potentially do. We talked about secure communication, distributed computing, but there's so much more to explore.
Oh, absolutely. Earlier you mentioned advancements in atomic clocks and telescopes. I'm curious to dive a little deeper into that. What kind of advancements are we talking about?
So imagine atomic clocks so precise that they can actually detect tiny changes in gravity. That would be huge for understanding things like earthquakes or even dark matter. And then with telescopes, we could be talking about peering deeper into space than ever before, unlocking secrets about the early universe.
It's incredible to think about the ripple effects a quantum internet could have across so many fields.
It's not just about specific applications either. It's about a fundamental change in how we think about information and communication.
I like the way you put that.
Imagine a world where information can be transmitted instantly, securely, with computation only limited by the laws of physics. I mean, that's the potential we're talking about here.
It's pretty mind-blowing and honestly a little intimidating too.
You know, it's true. But with every big leap in technology, there are challenges and opportunities. And it's up to us to make sure that this technology, as it develops, is used responsibly.
Couldn't agree more. Speaking of challenges, we were talking earlier about some of the hurdles in building this quantum internet. Like, how do you transmit those fragile quantum states over long distances without messing them up? It seems nearly impossible.
It's a big question, and researchers are working on a few different approaches. One of the most promising ones is the development of quantum repeaters. Now, unlike those classical repeaters that just make copies of the signal to amplify it, quantum repeaters need to work their magic without actually disturbing the quantum state. It's tricky.
It's almost like trying to, I don't know, whisper a secret down a long line of people without the message getting distorted along the way.
That's a great analogy. One way to do this is through entanglement swapping. You're basically creating a chain of entangled qubits, each one acting as a sort of relay station.
So it's like a series of quantum handoffs passing the information along without ever actually looking at it directly.
Exactly. And because the information is never directly measured, it's way less susceptible to noise and disruption. Pretty neat, huh?
That's so clever. It seems like so many of these solutions rely on entanglement in one way or another.
You're absolutely right. Entanglement really is the backbone of this whole quantum internet idea. It's what allows us to do all these crazy things with communication and computation.
It's just fascinating how something so counterintuitive can be so powerful, you know?
It is, isn't it? And it really shows you how quantum mechanics is pushing the boundaries of our understanding of how the world works. It opens up all these new possibilities we never even thought of before.
Okay, so we've talked about transmitting quantum information, but what about storing it? How do you keep those super delicate quantum states, stable for any length of time?
Another great question. And that's another key piece of the puzzle. Remember those quantum atomic disk drives we talked about? The ones that use clouds of cesium atoms to store entangled states.
Yeah, like a quantum hard drive.
Exactly. It's mind-blowing, right? And there are other promising techniques, too, like using those special diamond crystals we mentioned earlier. They can actually hold quantum states within the spin of a single electron. It's amazing how stable and reliable that makes them.
Diamonds and quantum information storage, that's a combination I never would have thought of. It really speaks to the ingenuity of the people working in this field.
Oh, absolutely. It's incredible what they're coming up with.
It strikes me is that building a quantum internet, it's not just a technological challenge, it's a conceptual one too, right? We have to completely rethink how we understand information and communication at the most basic level.
You hit the nail on the head. And that's what makes this whole area so exciting. We're not just building new gadgets, we're expanding our fundamental understanding of the universe and our place in it.
I love that. Now, speaking of expanding our understanding, let's loop back to the quantuminternet.pdf document for a sec. You mentioned that it had a lot of discussion about nuclear energy and thorium reactors. What were some of the key takeaways that stood out to you?
Well, one of the main arguments for thorium reactors is their potential for, really cutting down on nuclear waste. Traditional uranium reactors, they produce a lot of long-lived radioactive waste. But with thorium reactors, the waste decays much faster, which makes that long-term storage issue less of a headache.
That's definitely a plus. What about nuclear proliferation? Is there a risk that thorium could be used to make weapons?
It's a valid concern, but it's important to note that thorium itself isn't fissile. That means it can't sustain a nuclear chain reaction on its own. However, it can be converted into uranium-233, which is fissile.
Hmm. So there's still a potential risk there then.
Well, yes, but it's significantly lower than with traditional uranium reactors. You see, the U-233 produced in thorium reactors is usually contaminated with other isotopes that make it really hard to weaponize. Plus, as we touched on earlier, the decay products of U-233, they emit these high-energy gamma rays that could actually fry the electronics in a bomb. And those gamma rays are pretty easy to detect, which makes weaponization even more difficult.
So it's not a perfect solution, but it sounds like thorium reactors offer a much lower proliferation risk overall.
That's the general consensus among the experts, yes.
I remember the document also talked about pebble bed reactors as being a potentially safer alternative. Can you remind me how those work again?
Sure thing. In a pebble bed reactor, the fuel is contained in these tiny graphite spheres, kind of like tennis balls, and these pebbles are constantly moving through the reactor core, generating power.
So it's like a giant gumball machine, but filled with nuclear fuel.
Uh-huh, I love that image. The really cool thing about this design is that it's inherently safer than traditional reactors.
Hmm.
Because the pebbles are always moving, the heat gets distributed more evenly, so you don't get those dangerous hotspots that could cause a meltdown.
That's impressive.
Hmm.
It seems like pebble bed reactors have a lot going for them in terms of safety and efficiency.
They definitely do, and they're just one example of how people are innovating in the field of nuclear energy. There are all sorts of new reactor designs out there that could really help us meet our energy needs in a clean and sustainable way. But let's switch gears for a moment. I'm curious to hear your thoughts on what a mature quantum internet might actually look like, once all the pieces are in place.
That's a great question. We've been talking about all these building blocks, but it's hard to picture what it would be like to actually use a quantum internet.
It's true, we're still in the early stages, but we can start to imagine some of the possibilities. Picture a world where quantum computers are as common as smartphones are today, all linked together by this vast network of entangled qubits.
So instead of sending emails or text messages, we'd be sending qubits back and forth.
Exactly, and because those qubits are entangled, communication would be instantaneous and perfectly secure. Imagine video calls with zero lag, financial transactions that are completely unhackable, scientific collaborations that can share data in real time no matter where they are in the world. The possibilities are pretty mind-blowing.
It sounds like a world of ultimate connectivity and security. What would happen to regular computers in this quantum future? Would they just become obsolete?
I don't think so. It's more likely that classical and quantum computers would work together, each one playing to its strengths. Classical computers are still great for everyday tasks, like browsing the internet or editing documents. But for those really complex calculations, simulations, and data analysis, quantum computers would be king.
So it's about finding the right tool for the job.
Absolutely.
Okay.
And just like the internet completely changed the way we communicate and access information, a quantum internet has the potential to revolutionize countless industries and basically every aspect of our lives.
It's both exciting and overwhelming to think about all the possibilities,
Yeah.
But let's not get too ahead of ourselves. There's still a lot of work to do before we reach that quantum future.
That's true, but the journey itself is just as exciting as the destination. Every breakthrough, every new discovery brings us closer to realizing the full potential of this incredible technology.
Well, I think we've officially hit information overload for today. We've covered so much, from the bizarre world of quantum mechanics to the potential of a quantum internet, and even the power of quantum computing. It's been quite the deep dive.
It really has, and I hope our listeners have enjoyed the journey as much as we have.
I'm sure they have. But before we wrap things up, I want to leave them with something to think about. A question that will keep their minds buzzing about the future of all this quantum tech.
I love that idea. Okay, let's see. We've talked about how a quantum internet could revolutionize communication, computation, maybe even our whole understanding of the universe.
Right. And we've explored these weird and wonderful concepts like qubits, entanglement, and all the challenges of actually building a network that can use them.
So here's my question for you, dear listener, and it builds on everything we've discussed today. If a quantum internet can allow us to manipulate information at the atomic level, what other impossible things might become possible in the future?
Whoa, that's a great question. It really gets you thinking outside the box and considering the bigger picture.
Exactly. What kind of breakthroughs might we see in medicine, materials, science, maybe even space exploration? The possibilities are, well, pretty much limitless.
It's a future full of promise and also a lot of unknowns. But one thing's for sure, it's going to be an incredible ride.
I couldn't agree more.
So to our listener, we encourage you to keep asking questions, keep learning, and keep pushing the boundaries of your own understanding. This quantum world, it's vast, and it's always changing. And who knows, maybe you'll be the one to make the next big discovery.
It's really amazing to think about all the things we've talked about today, like unbreakable encryption and even, teleporting information. It really feels like we're on the edge of some kind of, I don't know, a whole new technological era.
It really does, doesn't it? And I think one of the most exciting things about this whole field is that we're really just getting started. There's so much more we don't know, so many mysteries still out there. That's what I find so fascinating. It's not just about learning new things. It's about pushing the boundaries of what we thought was even possible. It's almost like science fiction is becoming science fact right before our eyes.
Uh-huh. I know what you mean. Remember how earlier you were talking about teleporting information? Well, imagine if we could actually teleport energy or even matter, all based on these crazy principles of quantum mechanics.
And that would be revolutionary. I can't even wrap my head around what that would mean for, well, for everything.
It's true, and it really shows you how these advancements in quantum information, they could have such a huge impact on, well, on practically every other field you can think of. Medicine, energy, space exploration, you name it.
It's like opening a door to a whole new world of possibilities. And, you know, some people might find all this quantum stuff intimidating, but I honestly find it kind of, well, empowering.
I get that. It's like we're getting this sneak peek behind the curtain of reality, a chance to see how the universe works at the most fundamental level. And the more we learn, the more we realize just how much more there is to discover.
Speaking of discoveries, I want to circle back to something we touched on earlier, quantum computing. We talked about how it could potentially solve all these complex problems, but I'm curious, how does it actually work? What makes a quantum computer so different from, the regular computers we use every day?
Well, a regular computer, it uses bits, right?
Yeah.
Which can be either a 0 or a 1. But a quantum computer, it uses these things called qubits. And a qubit, it can be in a superposition, which means it can be both a 0 and a 1 at the same time.
So it's like each piece of information has, I don't know, a much wider range of possibilities.
Exactly. And this lets quantum computers do calculations in parallel. It's like having millions of regular computers all working together on the same problem.
That's incredible. So it's not just about speed. It's like a whole different way of thinking about how to process information.
Exactly. And this makes them really good at solving certain types of problems that are just too hard for normal computers. Things like breaking encryption codes or simulating complex molecules.
So that's where the potential to, revolutionize things like medicine and materials science comes in.
Exactly. Imagine being able to design new drugs or new materials at the atomic level, or being able to simulate these complex biological systems with incredible accuracy. Those are just a few of the things that quantum computing could potentially do.
Wow. It's mind-blowing to think about what the future might hold. But I know quantum computing is still in the early stages, right? What are some of the big challenges that scientists are still trying to overcome?
Well, one of the biggest ones is just building quantum computers that are large and stable enough to actually do useful work. Qubits are incredibly fragile, and any little disturbance can mess them up. It's a real challenge.
Sounds kind of like, I don't know, trying to build a house of cards in a hurricane.
Haha, that's a good way to put it. But researchers are coming up with some pretty ingenious ways to tackle this challenge. They're developing new types of qubits that are less sensitive to noise, and they're designing error correction codes that can help compensate for any errors that do occur.
It sounds like a pretty monumental task.
Yeah.
But the potential payoffs are, well, they're just enormous.
Absolutely. And the progress is really exciting. Every year, we see breakthroughs in qubit design, control, and stability. I really think it's just a matter of time before quantum computers become powerful enough to really make a difference in the world.
Well, I think we've officially reached our information limit for one day. We've covered so much in this deep dive, it's hard to keep track of it all. From quantum mechanics to the quantum internet to quantum computing, it's been an amazing journey.
It really has. And I really hope our listeners have enjoyed it, and learned a lot along the way.
Me too.
Yeah.
And to our listener, if you found this all as fascinating as we did, please keep exploring. There are so many resources out there to learn more about quantum information, quantum computing, and all the amazing research happening in this field.
And you never know, maybe you'll be the one to make the next big breakthrough.
That's right. The future is quantum, and the possibilities are truly endless. So until next time, keep those minds open, keep asking those big questions, and never stop exploring the wonders of the